So hi everyone, like you said, I'm Alex Gaynor and I'm working on a NumPy. How many people were here last semester and heard me talk about this? Okay, like half the room. Okay, so I am working on sort of the ultimate sort of set of projects. So I am working with the PyPy project, which is an implementation of Python. And NumPy is sort of a numerical and scientific computing toolkit that was originally developed for Python starting probably as far back as in the 90s, so it's pretty old. And Fortran plays into this, and you'll see how later. So if you're thinking one of those things is not like the others, less so than you may be thinking. So there's a tale of two Pythons. So PyPy is an implementation of Python, and of course there's also CPython, which is the implementation of Python probably just about everyone here who uses Python uses. So once upon a time there was CPython, and it was pretty good. And a lot of people used it, a lot of people still use it. It is where the language is defined, it's where new features are added to the language, and it's got like millions of users, really popular, really good. But it does have some problems. Its implementation is relatively simplistic, and so it's pretty slow. And so about 8 or 9 years ago, a couple of people started a project called PyPy, whose objective was to re-implement Python in Python and make it super fast. And so that's a pretty extravagant set of goals, but over the last couple of years, sort of the project has really come into fruition, and now there really is this Python interpreter written in Python that is significantly faster. But the Python ecosystem is not just defined by Python code, it's also defined by this sort of large third-party ecosystem code, a lot of which is not just Python, but which is written in C, because writing code in C is how you get fast code to run on CPython, basically. Python is slow on CPython, but if you put something in a C module, make an extension, you can get it back a lot of the same performance. And so NumPy is mostly one of these C extensions. It also has a lot of Python code as well, but there's a lot of C, especially in its core. And like I said, NumPy is this scientific and numerical computing toolkit. It has things like all sorts of n-dimensional array classes and matrices, and the ability to do sort of all sorts of operations that scientists care about. I'm not a scientist, I'm like a software engineer. I have absolutely no understanding of why these various operations are significant to people who do bioinformatics and quantum finance stuff and chemistry and physics and all these other fields. I have no understanding of why it's important. But I get that scientists like all these APIs that NumPy has. And so for a lot of scientists, NumPy is replacing MATLAB and R and sort of this other sort of set of toolkits that are mostly not open source and not free and hopefully not as good as well. So there was NumPy, and scientists think it's good. The rest of us don't really understand it. And so a couple of years ago, probably about a year at this point, the PyPy project started to re-implement the C core of NumPy in what we called NumPyPy. And so last semester I was here, and when I started talking to you guys last semester, we had one-dimensional array of floating point values, and that was basically it. And by the end of last semester, we had n-dimensional arrays of floating point values with 32-bit floats or 64-bit floats and integers of all sorts of different types, and more operations, and just generally the feature set was significantly expanded, and we actually had a lot of NumPy's features. In theory, we have like a third of the public API of NumPy implemented. Whether that's 1/3 of the commonly used API, that's a bit hard to say. But we had about 1/3 of the API, so we made really, really significant progress. So we think this is pretty swell. But there was also Fortran. So for reasons that also go completely beyond my understanding, scientists love Fortran. They have lots of code written in Fortran. They believe Fortran is like the fastest thing ever. They will happily like email you a 20,000 line Fortran file. They love their Fortran. And so part of this ecosystem is not just the Python code and not just the C code, but this other ecosystem of scientists have all these Fortran and C libraries that interface with data. And the way NumPy integrates with these is they have this wrapper that basically emits C code that calls Fortran, which then interfaces with Python. And so that, A, it's like the world's scariest thing, but B, it's not really convenient for us because it generates C code that works with CPython C API, which is not PyPy's C API. So we needed a new route in terms of how do we integrate with all this existing code that works with these C APIs. Yeah, so science like Fortran, I don't really think there are any programmers who started programming recently that do like Fortran. Maybe they do. It's kind of an interesting language, sort of. So yeah, so that's where we are sort of today, or at the beginning of the semester at least. We want to interface with Fortran, we want to expand sort of where NumPy is with respect to the rest of the community. So there's sort of three major goals I have for the work I'm doing this semester. And the first is integrating better with this Fortran community. So has anyone here who's worked with Python heard of the C-types library? Okay, a couple people. So C-types is probably the coolest and most underused thing in the Python standard library. It is a library that lets you load up any shared object you have on your system. So the MySQL library, Postgres' library, the math library, the C standard library, your Fortran libraries. You can load any of these shared objects and call functions in them. And that's pretty cool. So, for example, if you wanted to re-implement the sign function, you could load up the math library, part of the C standard library, load up math, and then call the sign function there. You can also load up these Fortran libraries and call into them. The trick is you just need to have something that exposes pointer addresses and the shape of the data and whatever other information Fortran uses. It turns out the really common representation for these arrays is the raw data, a set, the list of size of each dimensions, as well as strides, which are part of this really complicated mathematical formula. It's not actually that complicated, but they represent the distance in memory between two different ends of two different dimensions. It's not really important, but you have all these three major pieces of information. You need to expose them. So it turns out part of NumPy's API is every array has this sort of C-types attribute, which exposes all of its data as sort of basically pointers. Even though Python, everything's an object, basically we just expose numbers that happen to point into memory. And so the first part of the work this semester is exposing the C-types object so that we can have all expose basically this, and then we can take the wrapper generator that exists for the Fortran to C code and basically change it to be Fortran to Python with C-types. So in that way we can wrap these existing really scary Fortran libraries. The second major goal is also Fortran oriented. So people familiar with C, basically if you have a multi-dimensional array, you have what's called a row major order, which basically means if you have sort of two dimensions labeled 0, 1, 2, 3, 0, 1, 2, 3, so you have a 4 by 3 array of something. Basically, if you were to sort of go through memory sequentially, this would be 0, 1, 2, 3, 4, 5, 6, 7. So basically you iterate through each of the rows. For whatever reason, and where whatever basically means because it's more efficient for a certain class of applications, Fortran's default order is different. Fortran has what's called column major order, and these are also, the indexes are also numbered differently. I think Fortran starts indexing at 1, which is terrible, but so here we go 0, 1, 2, or 0, 1, 2, 3, 4, 5, 6. So as you can see, we're counting, we're iterating through each column instead. And NumPy has support for storing its data in both of these formats. When you create an array, you can say, I would like the memory here to be stored in C order or Fortran order. C order is the default because it means you're compatible with most C libraries and everything like that, and I think it's by and large more intuitive for a lot of programmers that have started with C. However, if you need to interface with a bunch of Fortran libraries, they expect all their memory to come in Fortran order. So the next major goal is taking sort of these, all this data and allowing it to work in Fortran order as well. So as I said, there's these three pieces of data: raw data, which needs to be in a different order, the sizes of each dimension, which actually stay the same, thankfully, and these strides, which represent the distance in memory, and those need to change because the distances change depending on which direction your columns are oriented. So that's the second major goal, is working with Fortran in terms of data storage and shape. The final goal is working better with sort of existing classes that subclass NumPy's array. So yeah, everyone's favorite meme, all the things. The array, it's an object drawing class, you can subclass it. This is what happens today if you try to subclass it. Subclass the array, it works. That's what creating an array looks like. It has 10 zeros. If you create the subclass, basically you don't even get the correct array back. You get the original class back. For those of you thinking that's got to be like a one-line change to change, so instantiating the class returns the right value. Yes, that's a one-line change. It's all the other operations that also return the different class. So, for example, if you take a slice of an array, you get back a view on the original memory. It also comes back as the subclass of the current array. And there's all sorts of sort of various rules. If you add two arrays, you do a pairwise addition on each of the elements. But which subclass do you return if, say, you're at an X and a Y, which are two different subclasses? There's all sorts of complex rules for sort of how they integrate. But subclassing is pretty common. For example, NumPy ships a pure Python matrix class, which is really just a special subclass of array that's limited to 2 dimensions and has sort of a set of extra operations. So matrix multiplication is not a pairwise multiplication by elements, but it's matrix multiplication. And sort of, there's all sorts of other things like that. So this is sort of the final major goal, is integrating properly with these subclassing rules so that we can start to bring in more of the pure Python NumPy. The big advantage for us is as we have sort of more of the core implemented, we sort of automatically get for free all of this pure Python code. And so that's sort of the biggest goal for this semester, is integrating better with this community and being able to leverage all of the existing code so that when we say we've implemented NumPy, we know that this doesn't just mean somebody who happens to write using the tiny subset that exists in NumPy works. It's anybody with this community and this ecosystem of Fortran and C and any other insane libraries. Anything they've written sort of comes under this umbrella and works within the system. So thank you guys very much. And questions?
Yeah, most of the code of Fortran code is written in Los Alamos National Lab. Most of the code for that nuclear reactor, nuclear bombs, and that's a heavily used Fortran.
Yeah, scientists love their Fortran.
Yeah. This has nothing to do with your actual presentation. Are you the guy who wrote the blog post about transactional memory on the PyPy blog?
No, I'm not. That's Armin Rigo.
Yeah. Okay.
What make you feel bad?
No one is Armin Rigo. Armin is one of the creators of the PyPy project and easily one of the most brilliant people I've ever met. He, in addition to creating PyPy, created the first Python JIT, Psycho, which is no longer really maintained, but for a while was the only Python JIT. He's also created the original SVN bindings for Python. He created the original Greenlit library, which is a way to do continuations in Python. He has his fingerprints in all sorts of awesome things. So, no one's Armin. Sorry. Stuck with me.
So I've used C types, but I have no idea how it works. How do you just throw a compiled shared object at it and it just does its thing?
So it's built on top of, both CPythons and PyPy's C types are built on top of libffi, which is a C library that basically handles all the heavy lifting. But basically, for all 3 major platforms, Unix's OS X and Windows, the binaries have a pretty stable file format. So on Linux, it's ELF, which basically means if you know how to parse this data out, it shows you it's basically at a table of stuff in the file. Here's where each function lives. If you know where the function lives, calling it is just a matter of knowing what the platform's ABI is and where you need stuff in memory and registers to call it.
Okay.
Yeah. Cool. Well, thank you guys very much.